go boop boop.
I literally hit record right before you said boop boop. So my wife's over here boop booping during the video. Anyways, hey, welcome back, Mustangs, to another edition of No Here, No Problem. Today we're going to be working on polynomial functions of higher degrees. I just want to let you know, this morning I actually woke up laughing. I must have slept funny. Anyways, moving on to polynomial functions of higher degree. What? I just tell a little funny joke. What? What do you want from me? Get them laughing. So anyways, we're going to be talking about polynomial functions of higher degrees. We've started off this unit talking about quadratics. Now we're talking about polynomials that have like a second, third, fourth, fifth, sixth degree, and the behaviors of all those functions. When we're talking about polynomial functions having only, they are functions that have only rounded curves. And so you'll see within the pictures that there's going to be like a bunch of maxes and mins, and we're going to talk about the behaviors that take place of these functions, about how many maxes, how many mins, what's the behavior at the ends of our functions, versus when we have not a polynomial function, such as an absolute value. This is not considered a polynomial function because it's got sharp edges. Okay. So when we look at the leading coefficients of functions, there's some stuff that we need to talk about here, okay? First and foremost, when we look at a function, look at the degree, and when we have an odd degree, we should talk about this. Can be determined when we look at the function's degree and its leading coefficient. Okay. So let's look first at an odd function. All right. When we see an odd function, it's going to have a degree of something like x to the seventh or x to the fifth or x to the third. These are obviously odd functions. And the behavior that takes place in these is, first off, this notation right here might be brand new to you. And what I'm going to actually do is we're going to actually kibosh this. We're getting rid of that. This is the book's notation that they use. But we're going to talk about the proper notation that we're going to see in calculus. And I think we've mentioned this before. What we say is the limit, mess that up, the limit as x approaches infinity, the y value approaches infinity, okay? So this notation right here, we call this limit notation. This is a way of just actually describing the behavior that's happening with our graph on the right side and the left side, or as we're approaching a certain value. So for this one right here, what we're saying is look at the behavior of the right side of my graph here. As this graph is moving to the right, you can see that my graph is moving up. And so what this notation says is that as my x value moves to the right, my y value is moving up. Okay, that's what that limit notation means. So we're going to do the same thing with the other notation. On this one, we're going to get rid of this, and we're going to say the exact same thing. Just for the sake of time, I'm going to copy this, and we're going to make some modifications to it. This notation down here says that as my graph is moving to the left, so as my graph moves to the left, my graph is going down. And so the notation that's going to be modified here is we're going to say as the graph moves to the left, my graph moves down. So this right here says moving left, and this right here says the y value goes down. That's what that notation implies right there, okay? So anytime we have an odd function, you're going to notice that one side is always going up, the other side is always going to be going down. So pay attention to that when we're looking at odd functions. One side goes up, the other side goes down. They go opposite directions, so they go like this or like this. Versus when we have even functions taking place. All right, and I'm sorry, this is actually, this example right here shows both an odd function and an odd function on the left one. It's also an odd function on the right one. The difference is the leading coefficient in this first one here. The leading coefficient is equal to a positive value, versus when we look at over here, we have x to the seventh, x to the fifth, x to the third. These are always going to have a negative leading coefficient. We should recognize that because we see that reflection taking place in the graph, and the graph goes up and to the left and down to the right. Okay, let's get rid of these. Okay, let's move on to an even function. So when we look at an even function, we're talking about functions that are x to the second, x to the fourth, x to the sixth. The most common one that we're used to seeing is obviously a quadratic, which is x to the second. When we have a leading coefficient that's positive for these, we're always going to notice the exact same behavior, that the graph is going to be going up and to the left, and it's going to be going up and to the right. So as we move to the right, the graph goes up. As we move left, the graph goes up. So how do we state this in that limit notation? We're getting rid of these. This behavior right here, we would say the limit as my x value goes to the right, my y value is going to go to infinity. It's going to go up. And get used to writing these limit notations. I know it's a little bit wordy, but you'll get used to it. And we need to get used to this because we're going to be seeing a lot of it when we get to calculus. Okay. This behavior, as my graph moves to my left, so as x approaches negative infinity, my y value is going to approach infinity. Okay. And obviously, if I go ahead and throw a negative in front of my even function here, so negative x to the fourth, negative x to the sixth, what's going to happen is we'll see my graph get reflected over, and we're going to see the graph actually now have the opposite going on, where instead of it going right and up, it's going to go right and down, and it's going to go left and down. Okay? All right, let's move on. I'm going to try to rush through these a little bit, and feel free to go back anytime you want. This can be a very long video. I'm actually planning on saving it into 2 separate videos, okay? The vertical direction that the graph goes as x increases or decreases is called the limit. Okay, and I've already mentioned this several times. You'll hear me keep talking about the limit. That again is talking about the end behavior of our graph. What's happening in my graph in the vertical direction as my graph goes to the right or to the left. All right, let's move on though to the leading coefficient test. So let's take a look at just some information that I can gather just from my leading coefficient when we're looking at these, okay? When we look at my leading coefficient right here, there's a few things that we can determine. That negative right there tells me that it's going to be reflected, okay? This 3 being odd tells me that the general picture of my graph, instead of it looking like this typical graph that we're used to, what's going to happen is that graph is going to actually get reflected over, and it's going to look like this instead. I'm going to actually move that back and put it here. And now when we look at the behaviors, we should see that the graph is now going up and to the right and down and to the left. Okay, that's what that little reflection going on there. Oops, I graphed that wrong, sorry. Let me get rid of that. And sorry, the graph will actually be in this direction now. Okay, it's going to be reflected. I reflected it the wrong way. I apologize. And so the graph now is going to be reflected, so it's going to end up having directions where it goes up and to the left and down and to the right. So as we go left, the graph goes up. As we go right, the graph goes down. The limit notation is the limit as x approaches negative infinity. So as the graph goes left, the y value is going to go up. And then the limit as my x value goes to the right, my y value, f of x, is going to go down to negative infinity. Okay, so this is the limit notation. Now just to confirm this, I went ahead and pulled up, our decimals here. Let me clear out some of the stuff here. And so you'll see we've got our first graph here, and I'm going to reset this so we can see it. You can see the graph goes up and to the left and down to the right. Okay, let's go on to our next graph, which is talking about zeros of a polynomial function. Now for this one, we don't actually have equations set up, so I'm going to actually take and relate all the definitions, everything we see, to a standard function that you guys are used to, which is just a quadratic function. So when we look at a function, a standard quadratic function, we say that f of x is equal to like x squared minus 8x plus 12. Okay? I'm pretty confident that all of you guys know how to factor this, but if we weren't aware of it, let's factor this out. We're going to have x minus 6 and x minus 2. Then we're going to have x minus 6 is equal to 0, and x minus 2 is equal to 0. We get that x is equal to positive 6, and we get that x is equal to positive 2. Okay? Now, there's a whole bunch of definitions that we have to talk about so that you're aware of what's happening throughout the rest of these problems that we're about to do. Okay? First things first, these values right here in this line, these are called factors. Okay? These values right here are called zeros. And then in this next line, these values right here are called x-intercepts. Okay? So you have to know the definition of each one of these because we're going to use them interchangeably. That we're going to say when I have an x-intercept, what I'm actually giving you is a 0. And then you're going to use those zeros to find the factors. Then we're going to use those factors to find the equation of the quadratic that actually generated the problem for us. So that's first, knowing those definitions. The second thing we need to talk about is right here where it says the graph of f has at most n minus 1 relative extrema. So what this means is n, when we're looking at this, is the degree. And so what this tells me is that whatever my degree is, I have always one less maximum amount of extremas that could possibly take place in any of my pictures. So if I had like x to the 5th, that means at most, I could have one less than this, which is 4 extremas. And again, the way or what we're talking about when we say extremas is we're saying either a maximum or a minimum within my picture. So we'll talk about what that looks like in some of these problems as we kind of start diving in, okay? Best way to handle these, let's just jump into some problems, really make some sense of all this, okay? So for the first problem here, we have f of x is equal to, and when it says find all the real zeros, we're saying find all the real solutions. We'll get into complex ones in the next section, but for right now, let's just focus on only real ones. Go through all your steps. Is there a GCF? Is it factorable? Do I have to use a quadratic formula? Is the leading coefficient not equal to 1? Do I have to use factor by grouping? Do I have to go ahead and do guess and check? Like, go through the whole process of all the possible ways that you can actually go through solving this. First things first, though, let's look for a GCF, which there is an x. That means we're left with x squared minus x minus 2. Factor this further, we're going to have x minus 2 and x minus 1. Plus 1, sorry. And then we're going to have x. Let me get rid of this. We're going to take those factors and set them equal to 0. We get x is equal to 0. X minus 2 is equal to 0, which means that x equals 2. And x plus 1 is equal to 0, which means that x is equal to negative 1. So we're going to have a 0 at 0, 0, at 2, 0, and negative 1, 0. Okay? Now, this is all the work that goes into it. Let's talk about each one of these parts so we better understand it. This 3 right here tells me that there are supposed to be 3 solutions. The degree always will tell you how many solutions there's going to be. And you can see down here, we end up with 3 different solutions, okay? When we look at the leading coefficient of this, the leading coefficient of this is a positive x cubed. Now think about what that graph looks like. We know that the graph is supposed to look something like this when it's an x cubed. If it was a negative in the front, we would actually see the opposite happening where the graph would actually look something like this. But I see it happening in the positive direction, so we know our graph is going to look something like this. When we look at my zeros for this graph, the zeros are at 0, 0, 2, 0, and negative 1, 0. So that means that the graph is going to have to look something like this in order to work. And from here, I could determine what are the end behaviors of this graph as well. I know that if I know the end behaviors, I can know which way it's going to actually be graphed. So I know that this has to go up and to the right, down to the left. If that leading coefficient had been negative, we would have a whole different situation where, given the zeros at 2, 0, negative 1, 0, and 0, 0, that the graph would have to go this direction to pass through those points. So let's confirm everything that we said was going to happen. Okay, let's look at Desmos here. We said that we're going to have these 3, oops, wrong ones. We said that we're going to have, this is my graph right here, sorry. And you can see that this is what the graph ends up looking like, and these are my 3 zeros right here at negative 1, 0, 0, 0, and 2, 0. Now I want you to look at this graph though. We have right here on my graph, we have a minimum. There's one extrema right here, and then up here, there's another extrema. So there's 2 extremas in my graph. 1 max and 1 min. And when we looked at the degree of this was 3, which tells us that we can have at most only 2 extremas. Okay? All right, that's it on that one. Let's go on to this next one. This one says, let's find a possible polynomial function for this. Let's find the possible polynomial function. So they give us the zeros here. They tell us that my zeros are at 4, 2, and negative 3. So let's go back here and let's look at these points. 4, 2, and negative 3. Okay, I'm going to zoom out so we can see all three of those points. And the question that we have now is, well, what's the graph going to look like for this? There's 3 points. There's 3 zeros in this picture. Let's figure out what a possible solution is for this. Okay, there's actually technically a couple different ways, but let's get the main one based off of only the information we have given. If I know that one of my x's is equal to 4, one of them is equal to 2, and one of them is equal to negative 3, we can take these values and actually work backwards to the original stuff. If I took this and wrote it out as a factor, it would be x minus 4 is equal to 0. Take this one and write it out as a factor, we'd have x minus 2 is equal to 0. Take this and write it as a factor, we'd have x plus 3 is equal to 0. Now, if I take those factors and continue working backwards and put them in together, x minus 4, x minus 2, and x plus 3 is equal to 0, we can see what's going to end up happening is that as I multiply these together, we're going to have x to the third power. And again, x to the third power either looks like this, or it looks the other direction where it's going to go like this. Okay? So let's continue on. What we're going to have to do is, since we're finding a polynomial, I got to multiply this whole monstrosity out. So this is where the hard part comes in. You ready? If I multiply out just this first part right here, I'm going to end up with an x squared plus x minus 6 is equal to 0. And this x minus 4 is still going to move down. Now I need to take this binomial, multiply it by the trinomial. I ask you to please be careful doing this, okay, and stay organized. We're going to have x to the third plus x squared minus 6x. Okay? That right there is just taking this x and distributing it to everything that we see over there. So x to the third, x squared, and negative 6x. Now we're going to take this negative 4 and we're going to distribute it to the trinomial that's over there. And that's going to give us a result of a negative 4x squared, a negative 4x, and a positive 24. And what we end up with is x cubed minus 3x squared minus 10x and plus 24. This is one possible outcome for this function. Okay? And just to confirm it, there's my answer, x cubed minus 3x squared minus 10x plus 24. Let's graph it. You can see that the graph clearly goes through all three of those points perfectly. Now, I told you there's more than one answer that can actually happen for this. And it comes from the fact that there's nothing stating an a value here. No a value is given to me. No value is attached to this coefficient to tell me whether it's supposed to be moving in the upward direction or downward direction. No value is telling me if there's a reflection taking place. And so I get a little bit of freedom here because of that. I could also take this and throw on here a negative if I wanted to. And by me throwing a negative on this, remember that's going to cause a reflection to happen. It will still have the same zeros, but it's going to be reflected. To prove it, watch this. I'm going to take and I'm going to put a negative in front of this entire thing. Let's put a negative here. And then let's put a negative at the, parenthesis at the end. And now let's graph it. And you'll see what happens is now the graph is reflected, goes the other direction, but still has the exact same zeros taking place. Okay? I could even put in here a negative 0.5, and what ends up happening is it still has the same zeros. I could put in here a negative negative 5, and that's still going to have the same zeros. All these values are doing is causing stretches and shrinkings to take place and reflections to take place, but it's not taking the graph and moving it side to side, so we're not changing those zeros at all. So unless there's an a value given, you have a lot of freedom for the answer, but you have to make sure that it multiplies out to at least give you this beginning polynomial that we have in this problem. Okay? So let's take a look at this next one here. Write an equation of a polynomial with zeros. So it says write an equation, there's multiple answers. Let's just use the most basic one that we can do based off of the information given to us. We have x is equal to 2. We have x is equal to 1 plus the square root of 3. We have x is equal to 1 minus the square root of 3. So there's going to be 3 zeros. That means we know what the graph's going to kind of look like. Let's go ahead and work backwards. We have x minus 2 is equal to 0. X minus 1 minus root 3 is equal to 0. X minus 1 plus root 3 is equal to 0. Let's combine these so that we're multiplying them out. We're going to have x minus 2, x minus 1 minus root 3, and x minus 1 plus root 3. And all that's equal to 0. Now I'm going to show you guys a little graphic organizer that we can use for multiplying out these really large quantities here, okay? When I have a trinomial times a trinomial, that means that we should end up with 9 terms being multiplied. It's kind of hard to do that, but there's a way we can actually keep all this neat and organized, and it's by using just a general Punnett square, just exactly like what you would use in biology. If I take the values we see there, x minus 1 minus root 3, x minus 1 and plus root 3, and you don't have to do this. This is just a graphic organizer for us to use. I'm using it. But if we multiply this out, we're going to have x squared minus x root 3. Continue on, we're going to have a negative x, a positive 1, a positive root 3. We're going to have an x root 3, a negative root 3, and then a negative 3. And that last one is a result of the fact that when I take this root 3 and I multiply those together, we're going to get negative root 9, and that's just equals to negative 3. So now let's put values together that go together. Okay, we're going to have an x minus 2 from the front there. The x squared is going to be on its own. The negative x is going to be now a negative 2x. Okay. These negative x and positive x root 3 are going to cancel each other out. So then, and this root 3 and negative root 3 will cancel each other out. So we're going to be left with a minus 2 here. Okay. Let's take this and now multiply the whole thing out. So x minus 2 times x squared minus 2x minus 2. Again, be careful. First, we're going to take this x and multiply it across all of these. So we're going to have an x cubed minus 2x squared minus 2x. Next, we're going to go ahead and take the minus 2 and distribute across all of this. So we're going to have a negative 2x squared, a positive 4x, and then a positive 4. Put everything together, we end up with x cubed minus 4x squared minus 2x and plus 4. Nope, sorry, plus 2x and then plus 4. So there's your function that has those 3 zeros. Let's check it just to be safe. I'm going to turn the last graph off and let's put the next one on. We've got these 3 points were my zeros. Let's make those labeled here. Okay, we'll get some wonky decimals obviously from those radicals that are there. Let's go ahead and graph my answer, and we can see that my answer does actually pass through all 3 of these points perfectly. Okay. All right, let's continue on here. So what about when we have repeated zeros? You know, we've all seen functions before where we might have a repeated factor. An example would be like if I gave you the quadratic that said x squared minus 4x plus 4, and I said that that's equal to 0. What ends up happening as I factor this is we get x minus 2 and then x minus 2. Now remember, this 2 says that we're supposed to get 2 answers for this problem. What ends up happening is I have an x is equal to 2 and an x equal to 2. And when we say that we have more than one of the exact same answer, we say that we have a multiplicity of whatever the number is. So I would say that x is equal to 2 with a multiplicity of 2 because it counts twice. Whenever this happens and we have an even number, you can see it in the directions here. Whenever we have an even, we call this a touching zero, or you'll hear us call it a crossing zero. Nope, not, sorry, wrong thing. Even, touches, and what we say that this is just a turning zero, not just a touching zero. We call this a turning zero. Okay, we'll talk about why that is in a moment. And then when the function is odd, it has an odd degree. It's always going to have crossing zeros. Those are zeros that are going to cross directly through the x-axis. So what's the difference between these? Well, a crossing zero means it looks something like this, where it actually crosses It actually goes directly through the x-axis, crosses it. Versus when we look at something like this, it's going to have a, whoops, that's a bad drawing, a turning zero. It comes down, it hits the x-axis, it turns, and it takes back off in the other direction. It can even start by going up, hitting, going back down, and away. So we're going to see several examples of this in a moment here. All right. So let's look at these and determine what are all the zeros and whether they're crossing or turning zeros. This first one here, when we solve, we get that x is equal to 0. This right here, since it's only counted once, this is going to be a crossing 0. The next 0 we're going to have is that x is going to equal -5. Now this has an even exponent to it, which means that this will be a turning 0. This right here, that -4, x is going to be equal to +4, and this 3 tells me that it's going to be a crossing 0 because it's an odd value. And if I ask you what's the overall degree of this problem, you should know that this is a 6-degree polynomial. And that's because that 2 means we write it out twice, and then a 3 that's there means we're going to write it out 3 times. Now, how do I know it's a 6-degree polynomial? Well, that's because at some point during my problem, all of these x's that we see here will get multiplied together. And you can see that I've circled 6 x's, and that means that it's going to be a 6-degree polynomial. Well, what does that look like graphically? Remember, 6 degree, x to the 6 tells me that it's an even function, and that tells me that the behaviors are going to be both going up or both going down. Since the leading coefficient on this is positive, it's going to be both going up. Let's see what this looks like when we look at the actual picture. Turn these off. Let's go to this graph. And voila. Now, this picture, you can't tell what's going on at this moment. Let me zoom and change everything so we can see it a lot better. Okay, this takes a moment. So I got to change all of this stuff so it stretches out so we can see it really nicely. Okay, there we go. So there is our entire graph with everything that we just discussed happening. Right here at this point, you can see that the graph hits, turns, and goes back. That's when x is equal to -5. You can see that right here, when we look at my graph, you can see that this crosses at 0. And you can see right here at +4, the graph crosses at 4, like we talked about happening. Okay? When we zoom out a little bit, let's look at all the extremas that could possibly take place in here. We said that there are going to be, and the behaviors, sorry. The behaviors, the graph, as it goes up and to the right, as it goes to the right, it goes up forever. And as it goes to the left, it goes up forever. So you can see it's that even function behavior. Look at the extremas. You can see that there's a couple different extremas taking place in this problem. You've got a minimum right here. You've got a maximum up at the top here. You got a minimum down here. And then you got another curve that actually takes place right here. Okay? Which I think if I was able to manipulate this better, I could probably get this to look more, at this spot right here, I could get to look more like an actual max or a min. But you get the idea, and you can see these are my maxes and my mins. There's at least 3, and there's this guy right here, which is a 0. Okay? All right, let's go on to the next one here. Let's look at, we have -3x to the third plus 3x squared. Let's determine how many zeros there are. We know there's going to be 3 zeros. Okay? We know that it's going to be an odd function because of that degree. Because it's a negative, we know the graph is going to look something like this. And so it might have 3 zeros that are like this. But let's see if those are crossing zeros or if they're turning zeros. So we have -3x. And because I can factor out, let's factor this out. We're going to have -3x squared. And then we're going to have an x minus a 1. Now this right here, -3x squared equals 0. If I solve for x, we're going to get x equals 0. But because it's even, it's going to have a multiplicity of 2. So this is going to be a turning 0. Even, multiplicity 2, it's turning 0. This right here, x minus 1 is equal to 0. That's going to tell me that x is equal to, I don't know what I just did there, that's a 1. And because this only is an odd 0, it counts once. This is going to be a crossing 0. So let's see what this looks like. A turning 0 at 0 and a crossing 0 at 1. Let's turn this graph off and look at this one. I'm going to reset it so it's back to normal. And you can see that we've got a crossing 0 at 0. We've got a crossing 0 at 1 and a turning 0 at 0. And then as far as the extremas go, there's one maximum in this problem and there's one minimum. So there's two extremas, which is one less than my degree. Okay? That is it. So for now, what I'm going to do is I'm going to actually stop the video here, and I'm going to make a separate video as we go in and start filling in all these different charts, because these charts are going to take a little bit of time. My recommendation for you is actually stop the video when you are actually filling these charts, then go back and watch the video so you can see if you're actually doing it right, okay? Until then, you take care, and we'll see you shortly.